Raina is writing some questions, but I'm going to start by talking about a couple of things on the DYU that y'all killed me on. Oh my gosh. It gave me a heart attack / stress / whatever else we want to call it. Yeah, how many times have you been killed? Too many times, but y'all kill me. All the time. Alright, some of these I think we can, we have already addressed or will address with other things. Ladies and gents, number 4. What type of data goes on a segmented bar graph? Categorical, okay? We got to recognize segmented bar graphs, mosaic plots, that's all categorical stuff. If we're talking about, what was it? The daily high temperature and the number of bird sightings, is that categorical?
No.
Those are both what?
Quantities,
okay? So, okay. I need us to understand that. Please don't ever miss that again, okay?
It won't happen.
Second, okay? Back-to-back stem plots, which we haven't done much with, which I don't think anyone picked that. Histograms. That is for quantitative.
What is that?
But how many variables?
One variable.
We need to recognize that these are for only one variable situations, okay? What's the only type of graph we've done in this entire unit?
Scatter plot.
We need to remember that a scatter plot is for, and I think someone, I don't know if it was here or somewhere else, that I saw someone write explanatory and response, but we have 2 variables, and they're both quantitative. If you have 2 quantitative variables, you've got to do a scatter plot, okay? 2 quantitative variables, it's got to be a scatter plot. If you got 2 categorical variables, what do we typically use? There's 2 options.
a segmented.
Segmented bar graph or a mosaic plot. Remember, segmented bar graphs and mosaic plots allow us to compare 2 quantitative or categorical variables. Scatter plots. We all good on that one?
Yes, sir.
Okay. I think that was only you in getting your DYU back. Is there any of these that you need to ask a question about? I think y'all actually did really well. Number 1, Kenzie. But just talk about multiple choice to start.
Oh, never mind.
Okay, so I assume there's a couple free response. Any multiple choice that we need to talk about? Yes, Ian.
Number 2.
Number 2, okay? Okay, so number 2 right here. What is being asked for?
The residual.
Okay. One thing I want to suggest, if you're working on a question like this, and they ask for something, some of us try to start at the very beginning instead of start at the end. Like, the end of all this, what do we want? A residual. So, start there. Like, and that sounds weird, but like start with what you're trying to get to. A residual, how do I calculate that?
Advanced place. I mean, y equals a equals actual minus.
Actual minus predicted. Right? We need to recognize AP, but actual minus predicted, okay? Do you know what the actual value is yet?
No. Oh, 25. Yes.
Because what we're trying to do is find that prediction. So the actually weighs this, so 25. Minus the predicted. Now, what do I need for that predicted?
The 20.
So if that 25 is my actual, the other thing to remember is it literally says y is the what? Predicted weight. T is the age. Isn't this the age right here?
Oh, see.
So we got to substitute 20 in for the time or to the age. So the predicted weight. This is also why I like to write out the variables. You could have done that to help you here. It's equal to 16.6 plus 0.65 times 1t. I don't remember what that was. Was it 29 something?
29.6.
29.6. So notice how this is over-predicting. We get a negative residual because the actual is below that prediction, right? 25 and 29.6. We're good with that now?
No, it didn't break into years.
Oh.
So I did 5, 6.
I was so wondering where in the world you got 5, 6 from. That makes way more sense now. But also, it tells you its age in months. Yes, right on multiple choice.
Yeah, no, free response.
We haven't gotten there yet. Any other multiple choice first?
Okay.
Okay.
Oh wait, you already did number 7.
We did number 7 yesterday.
Okay, I'm good.
Okay. And Dixie, I do have the video from yesterday uploaded, ready to go. Alright, we already talked about A, correct?
Oh.
On the free response, we talked about A and B and C and D. We didn't talk about E and F. Is that right?
That's correct.
That's correct, Raina?
So what I was confused mostly was to interpret slope. In the notes you said, for each additional AX context, the predicted Y context increases/decreases by slope. And I wasn't sure how to apply that in real life, so like
So what was the
additional
slope
one-
here, 2 point something?
8063.
8063.
So 1, so that is the change in the predicted weight, I think, right?
No. Yes.
Divided by the change in the chest girth,
Yes.
okay? For every extra, what is that centimeters?
Yes.
So for every extra 1 centimeter in chest girth, the predicted weight of the elk increases by 2.8063 kilograms. It doesn't have to be that exact wording, but it does have to be that exact concept of every extra 1 in the explanatory variable, change in that explanatory variable, the predicted change in the dependent variable is increasing or decreasing by this amount. So like, that's why, remember, I write this out to help me visually see what the change in X is and what the change in Y is.
Yeah, so I was confused about this. It's a DIU, so it will be, if I do well on the test, it will.
Yeah, I haven't updated y'all's last DYUs based on the last test, but yes, I reevaluate, yes. And so one of the things I do want to point out here is, again, you don't have to word it exactly this way, but you do have to have these exact ideas. You could have very easily said the predicted weight of elk, or the Rocky Mountain elk, is that what,
Yes.
that what this one was? The Rocky Mountain elk increases by 2.8063 kilograms for every extra 1 centimeter in chest girth, right? Like, the order doesn't matter, the concept matters, right? Like, the change in the predicted response variable in respect to that predicted, or not predicted, the change in the explanatory. One thing I do want to point out, because I noticed this in one student's DYU, I think, and I want to make sure this is clear for everybody. What was the equation here?
It was -135.51 plus 2.8063 times chest girth.
Okay. Please notice, I am not predicting chest girth. The only thing I'm predicting is the weight based on a chest girth.
So
You
why
don't
not
predict the input, you predict the output.
Must have been a win.
Must have been an iPad, right?
It's the first Monday, so.
So, the predicted output, we always predict outputs, we predict outputs, we predict outputs, okay? We do not predict inputs. We put inputs in to predict outputs. Okay, interpret are we good with that information so far?
Yeah.
Yes, Kenzie.
Can you go over E?
Yeah, I haven't gone over that one yet, yeah. So, interpreting R squared is one of those that you really have to either memorize how to interpret it or understand it and interpret it through the understanding. And the reason I bring that up is Mathematic, I think, does a good job of creating an interpretation for everything that always works. The problem is There is way too much in AP Stats to memorize everything. There is. But if you understand how things are connected, that's going to make things make more sense. So this value of r squared, remember that's my coefficient of determination. So I'm going to come up here really quickly. And so here is the graph for this, okay? I'm not sure exactly where the average weight is. I'm going to estimate the average weight to be here. Somewhere in that region.
It comes
Okay.
to the average weight.
Huh?
Mean weight, 231.
Where does it say?
Last sentence.
231.
Right here.
Oh, sweet, perfect. I didn't even read that. I was looking at the table. Oh, so I was pretty darn close. Okay, so there's my mean weight, right?
Right.
And if I look at the distance between each point, the vertical distance, and that mean, I can create a square off of this. In fact, remember when we calculate standard deviation of my y values or of the weight, it's going to be the square root of the sum of y minus y bar, the mean y squared divided by n minus 1, okay?
That's all.
So I'm just looking at these sum of squares, okay? When I look at these sum of squares, do you see all how big these squares are? And there's a lot of those squares, okay? However, if I take my regression line and I draw it through there, is the sum of squares going to be greater or is that sum of squares going to be less?
Less.
It's going to be way less. Like my points are way closer to that line than it was to the mean. Well, the question is, how much did we reduce that sum of squares by? That's what r squared is telling us. This is how much was the sum of squares, not technically, from the mean, right? So sum of squares from the mean, which we don't use this, but if we're talking about those sum of squares from the mean, what is that a measure of?
Percentage, how much is.
Hold on, you're trying to jump to the coefficient of determination. Listen to the question I'm asking. What is the sum of these squares a measure of? Like what in general is it measuring? When I say a measure of in statistics, let me clarify. Is it a measure of center or is it a measure of spread? That's the spread, right? Like it's coming from these differences, right? How far are we from the measure of center? So the question is, how much was the sum of squares from the mean? That's my spread or variability. Spread or variability. So how much was that sum of squares reduced by the least squares regression line? That's what we're answering with the coefficient of determination. How much was that sum of squares from the mean, that variability, how much was that variability reduced by the least squares regression line? And so, when we did 1 minus, and so remember I told you like the best way to calculate r squared, like obviously you can take r and square it, but the best way to calculate r squared is 1 minus the sum of squares from the residuals, because notice the residuals would have a really small sum of squares overall, right? Divided by the total sum of squares coming from the mean. So like this formula is telling us how much that sum of squares was reduced by. So when we say r squared equals 86.5, by the way, when you calculate r from this, please make sure you write it as a decimal. R has to be between -1 and 1. I had a few of us get 9 point something for the r because we took the square root of 86.5 instead of 0.865. Okay, so be careful. So r squared though is equal to 0.865. You take square root of that. But what is that really saying? 86.5% of the what?
Variability.
Variability. So of the variability in elk weights, right? So there's all this variability around the elk weights, right? There's that huge sum of squares around the average elk weights. So 86.5% of the variability in elk weights is, we can say reduced or
Explain.
explained by the, remember a least squares regression line is a linear relationship
With the chest curve.
with chest curve. I don't know if that's exactly what mathematics says or not, but that's getting to the heart of how much was that sum of squares reduced by? How much was that variability explained by this linear relationship? That's what we're talking about with coefficient determination. 86.5% of the variability in elk weight was explained by the linear relationship with chest curve. Star has had his hand up first, then Raymond. Star. Go. I'm sorry. Right.
It's more like a request. I think I already did all the homework for this, for like interpreting the R squares, this part. Is it okay? Is there any way to have extra practice?
There is, I know for sure there's some in the textbook. I can look to see what pages it's in the textbook, and I believe I have an answer key in this book already, so let me see for a second. So R squared is in the section 2D, I believe. Maybe 2C, hold on. 2C. R squared is in 2C. Yeah, there it is. So if you look in section 2C, there's some questions like, it's like at the end of the lesson, right? There's literally a section that's titled Interpreting R squared in S.
Is it for new one or old one?
This is for the new one. If you have one of the older ones, I can look at it and show you where it is. But yeah, it's going to be in that section of the book. So there's some good practice there as well. But again, I will say, like, this is one of those where just taking the time and like you could write the problem down on a separate sheet of paper and redo it. It's going to follow that idea of the percent of variability in the response variable that is explained by the linear relationship with the x variable, right? The explanatory. Yes.
I was more reading up to get key for saying that 86.5% of the data on chest curve predicted weight can be explained.
I'll have to look at that more closely, but one of the things I do need to point out, it's not 86.5% of the data, it's 86.5% of the variability. It's all about that variation.
Okay.
So you can say variation or variability, something to that effect. So hopefully, does that help E make more sense? I know we need to talk about F still. Yes? Are you just stretching really good? Really well? Sure? Okay. I'm not as sure by that face, but okay. F, really quickly. So, calculate and interpret the residual of the elk with 132 centimeter chest girth and weight. I don't know for sure, but I think for the most part everyone was pretty okay with calculating the residual. Maybe a couple of small mistakes in there. I will say there was someone who consistently calculated the prediction wrong. Just be careful when you type yourself into the calculator, because I don't know how that happened. Was it you? Do you know what you did? Okay. But like, if you type that back, try typing it back in, because like, you knew how to do it. You had everything substituted in right, but then the calculations were wrong. But just keep that in mind, be careful. So what was the predicted weight for this elk?
234.922.
234.922, okay? And then don't forget, like if I want a residual, it's advanced placement, right, Star?
Yes.
Actual minus predicted, or y minus y hat. So actual was 210 minus 234.922. So what is that telling us? Like, what is the fact that that prediction, or what is this value telling us about our prediction and the original weight, or the actual weight?
The actual weight was 24.
Guys, one at a time, please.
It was 24.9216 below the predicted weight of elk.
Be careful though.
Oh.
There's
No,
something you're
minus.
missing.
Yeah, I was confused. I didn't know what to put after 24, after the number.
So
Well, it's kilograms still. But which elk are you talking about? Is that true for every elk that we're looking at?
Oh,
That
just
is
the,
the weight.
the one given.
Which one's given?
The red.
Oh,
Yeah, the elk with a 132 centimeter chest girth. And I would also include the original weight. Personally, I don't know, I can't remember on the AP exam they require that or not, but I would put it. Because it's this elk, right? It's an elk with this chest girth and this weight is 24.922 kilograms below what? What is predicted?
weight.
Thank you so much, I'm sorry.
That's how we interpret it. Like, and I think, I'm hoping we're starting to pick up on this. Yes, we gotta do some calculations, but what's more important than just numbers? The context. Like, what does this thing mean?
Yeah, I'm sorry.
Like, that's the whole point of statistics. I actually had a student of mine who graduated the year COVID hit,
Jeez.
which this doesn't normally happen, but he messaged me on Facebook last night, and he was like, Mr. Kenny, I'm like really glad now that I did this, because now when I see people make claims, I'm able to like cut through the bull crap and like look at, say, what does this actually mean? And that's what stats is all about. Like, statistics is the most real world math you can ever study. Technically, it's not really a math, but we'll get into that later. But yes, it's mathematical science, right? But it's the most real world application of math that you're going to study in high school. But that means we have to put it in the context of the world. How does this inform me about the world? Okay, that elk is, this elk specifically, is 24.922 kilograms below what is predicted. Danny, you had your hand up, and then Madeline.
So, what I was confused, I think since we should go over this one. So when you say below and above, so the value, when you say below, probably the value is going to be negative.
Noted, so think about it this way. This is my actual value, right?
Yes.
So that's, say, just right here overall. This is what was predicted, right? So to have that value, isn't this actual weight below what was predicted for that elk?
Yeah, what I'm asking is, should I say, so the value was negative, should I say negative 24.921?
No, it's just
below.
24.922
Yeah.
below.
Yes, got it.
Just like with z-scores, when I interpret that z-score, I'm not going to say it's negative 1.5 standard deviations below. I'm just going to say it is
That amount
1.5
is
standard
below.
deviations below the mean, right? So, you're okay. And then Madeline, you had a question.
I just did it backwards, even though I did the predicted value is
Totally fine.
something else.
Just like I said earlier, with interpreting slope, it doesn't matter the order, it matters the concepts. The predicted value of the elk, well, how did you word it?
The predicted value of weight of a 132 centimeter girth was 24.922 kilograms above the actual value.
Oh, I see what you're saying. Yeah, so you focus on the predicted weight being above the actual. It's saying the same thing. It's just this is a little bit more traditional because we do like to compare to the actual weight, right? Like, but yeah, so Madeline just interpreted it through the context of the predicted weight being above the actual weight, which is true as well, right? Like that's a fine way to do it. We just typically want to compare to the actual weight. Yeah. But notice that's why, like, draw a quick little graph.
Right.
With normal distributions, what I always tell you to do,
Normal this.
draw a quick little graph before you try to put normal distribution in the calculator. Yes, it is hard to visualize these numbers sometimes, and even still, sometimes when I get to a negative, I have to think to myself, crap, does that mean I'm over or underestimating? But then if I look just at the original numbers, it's an easy tell.
Right.
If I look at a quick sketch of the graph, it's an easy tell. So like, don't try to just memorize every single detail because there's, again, too much to memorize. But a visual representation, drawing it out like this, can really help explain what's happening. Like, visualizing what's there, or drawing it out to help you visualize what's there. Okay. Trying to remember on true false, but we got to get going. I think I didn't have a whole lot to talk about. Because most of this we did talk about yesterday. Okay, let's get into the lesson for today. We're gonna have to move a little quickly. There was a question about homework 3.42b, not sure about the curve pattern. What does COS mean?
Cosine.
Cosine.
That's what it looks like.
It looked like a cosine graph, and is it appropriate to include it? I just wanted to describe what exact pattern the residual plot the graph had.
Hold on one
So-
second, hold on. I need to be able to look at the graph, the thing, before I start telling you stuff. Alright, it's 3.4 homework.
Yes.
Number which one?
Number 2 and B.
Alright. Load a little bit faster, please. Okay, 2B you said?
Yes. 1B. Huh?
But you said 2B.
Yeah, 2B. Yeah. I'm sorry. Yeah.
You're overcomplicating it. There's a curve pattern.
That's
A
a.
linear model is not appropriate.
Okay.
Yeah, you don't have to go to the level of what type of pattern is there. It just says, is a linear model appropriate? And yeah, I mean, you could say maybe sinusoidal or cosine. You can also maybe say a cubic, but don't stress that. Is it scattered or is there a pattern? There's a pattern in the residual plot, so a linear model is not appropriate. Right? It's like that's all you have to talk about there. Okay.
Mr. Kenny, now you this is the unit 2 part.
Yes, hold on to that for a second. Is it okay to submit prayer model on Thursday? Yes. Check your understanding 3.3 part B. Do I have? Alright, I'm just gonna pull up the answer key just to make this life easy.
Say that to your
So 3.3 part B, that's this one. Is this the question you were asking about? Okay, so what do we have to do? Does the y value, the y-intercept have meaning in this context? I mean, it does. So when Michael runs 0 miles, the predicted number of calories burned is 20 calories.
Is that extrapolated?
I see what you're saying. So, I mean, do you understand how off of the model to write that? Okay. But I mean, like, you burn calories by standing.
Right. Like one.
Your body, like, by generating heat, your body burns calories. By existing, your body is going to burn calories. But apparently when he runs, he burns about 160 calories per mile, which that's a little high. But yeah, just even if he doesn't run a mile, he still burns 20 calories. I would assume it's supposed to be, yeah, I don't know. But yeah, when he runs 0 miles, the predicted number of calories burned is 20. That's it. Okay. All right. Okay. Now we're gonna get started with today. So we got 15 minutes to get as much done with this lesson as possible. Okay. So what we're about to do is the second half where we talk about horizontal versus vertical outliers and potential outliers in bivariate data and potential influential points and how they affect the least squares regression line. So what, yes, this is 3.5. Yep. 3.5, what we have to do is we mostly, with bivariate data, just have to know how it's going to affect a least squares regression line. So, tinyurl./regression applet, let's do it. So what we're going to do is I'm going to manipulate it on here for the sake of time and then have you kind of discuss a little bit. tinyurl.com.
I'll take it.
That's not how you spell applet. Is it gonna approve? Okay, cool. Thanks, county system.
Are you out of breath?
Sorry, you're overstimulated.
I did not mean to pass that.
Oh, that's fine, because that's very.
Start. We're the ones that make it like my blood pressure rise. I'm like, you're like,
That's fine, that's fine.
I did not mean to.
maybe put a cake.
Did you see that?
We'll see what it is.
No, that's not what I want.
Greg might have thinking like,
Yeah.
She thinks you just did that, I mean, what you want for your own.
I didn't write it.
This applet is no longer here.
I put my stuff down straight.
Guys, can we sit down, please?
Thank you, sir.
That's enough side conversation, guys.
I can't find words.
Especially if you're a junior, I expect that. Oh my gosh.
I wish I could go there.
Yeah, seems too.
John Woods booth.
Seniors.
Sorry, I started spreading rumors about that.
Oh,
To me,
Like, get ready for scandals.
well, I found out they don't have it as an applet anymore. They only have it in Desmos. Don't know why they got rid of the applet, but thank you, I appreciate it. Okay, so there's our least squares regression line. What does it ask us to other shenanigans? That sounds wild. All right, so predict if the slope, the y-intercept, and correlation will increase, decrease, or stay about the same, and we're going to check our prediction. So what I want you to do is look at your graph, talk with your small group for just a little bit, and I just want you to make a prediction how each of those added points will affect your slope, your y-intercept, or the correlation value, okay? All right, so just make a quick prediction, not very long. How do you think it'll affect those things?
3.5. That one.
I think this.
About B there?
No, sir.
Okay. All right, let's give you another minute or two to talk about C and D, and then we're going to talk. You had a question.
I think it's A first.
So it's like the slope went down. It's down to 0.22. The y-intercept is definitely higher than the actual. Okay. So it is a less linear relationship than it was. Okay.
Couple little squiggly lines.
What about for
Yeah, we're not bringing the
I
model.
think that's what we're doing.
For C, interpret would go.
I did.
Oh my gosh, I see.
So let's look. Hey guys, let's look at point C. Okay. So point C. Tell me if I'm right. All right. So remember, I'm going to delete this point. Okay. Deleting that point. I'm back to here. Point C is kind of in this area, isn't it?
Yes.
Okay, so make sure you pay attention to that slope. That's almost 0.9. The y-intercept's 1.5. R is 0.9553 right now. Where did? Yeah.
They don't want you to
The
add the
slope
point.
increase.
Well, I'll just put it here. Okay, so here is roughly where it is. What happened to my slope and my y-intercept?
It decreased by.
It decreased, but how much did it really decrease by? It didn't really decrease much at all, did it?
Yeah.
Okay. How much did the y-intercept really change by?
Down.
It went down a little bit, but how much did it really change?
Not much.
Not much, right? So what I might say here is the slope and the y-intercept are almost the same. What changed though?
Correlation.
Correlation. Notice if I move this point further down, how much the y-intercept and the, like if you look at that line, how much is that line moving?
Not for real.
Not for real. The slope is staying almost the same, but if I move that point down, I will point out what's the y-intercept doing?
It's
Going down.
It's going down, right? So we're talking about why that's the case in just a second, but I need us to mostly recognize when we had points way out here, what did they affect? The correlation, it affected the
Everything.
y-intercept, it affected the slope. But when I am looking here vertically, right,
Right.
that point's pretty far away from these data points, but is it really changing the slope?
It's really not.
It's really not. Is it, when we go down, what's it doing to the y-intercept?
It's making it lower.
It's shifting it down, but what's it really affecting?
The R.
The R, the
correlation.
correlation, right? What about when we go significantly above?
Not for real.
How much is it changing my slope?
Not much.
Not much. What's it doing to the y-intercept?
Not much.
Not much, but is it going up?
Yes.
Yeah. Notice if I keep dragging this point further higher, what's going to happen to the y-intercept?
Up and up and up.
It's going to keep going up, okay? But what's happening to R?
That's changing drastically.
It's changing drastically. What does question 3 say? So, why are points A, B, C, and D considered outliers?
They're outside that way.
It changed the overall correlation.
Yeah, change the overall correlation. What were you saying though, Charlie?
It's outside that cluster of data that I think
It was
Remember,
outside.
outliers with univariate data, the outliers were far away from the rest of the data, right?
there's a gap.
So why do we call this an outlier? What? Because
Extreme values.
this point is far, or whatever the point is. So these points, I guess. These points are far
These points far.
from the rest of the data.
Is your video?
Yes.
How can we, I thought that if the slope is in the, looking at the, how it changes the slope, it will be really similar, correlation will be as similar with the change of slope. How can,
The correlation being positive or negative just tells if it's increasing or decreasing, just like the slope tells us increasing or decreasing. But notice like the slope didn't change much, but R did. Because what does R measure?
the correlation
But what is a correlation? It's telling us how strong
from
the linear relationship is. If this data point's way up here, slope's not changing much, but is that still a strong linear relationship?
Oh,
No, like that's changing how linear this relationship is. So these points are far from the rest of the data. Now I will remind you, we're calling them outliers right now, but on the AP exam, what are you not going to call them?
potentially.
You're not going to call them outliers, you are going to call them potential outliers, okay? Alright, so we need to recognize that for number 3. Number 4 though says which outliers had the greatest impact? The vertical ones or the horizontal ones?
The vertical.
So remember the vertical one didn't even really change the slope much, did it? It impacted the y-intercept very slowly, but the vertical ones impacted R. But didn't those horizontal ones drastically change the direction?
Oh, yeah.
The slope? Okay, so when we say number 4, last thing before lunch, we need to recognize horizontal outliers are highly influential on the least squares regression line. All of them affect R, but the horizontal ones influence the least squares regression line. Head on to lunch. We'll pick up with this after lunch. Yes, Trina. How do you interpret the slope in the y-intercept? Alright, so looking where we left off. So outliers. Quick notes. How are we going to define what an outlier is? So far outside
The rest of the data.
the
Center. The cluster.
rest of the data set. Okay. So any points that are far outside the rest of the data set, we're going to call that an outlier. Yes, Charlie.
How do you define what is far outside the data?
Fantastic question. We don't worry about that in AP stats. In AP stats, we just say it's a potential outlier.
Okay.
So if it is outside the general pattern, right? So if it seems like a deviation from the normal pattern, we consider it a potential outlier. We never prove outliers in bivariate data. Okay, yeah. That would be a pain. All right, high leverage.
here.
All over the.
Yeah, was that even in the lesson
No.
questions? Okay, so, oh, we say,
We had the answer.
do what? Oh yeah, it's in the textbook. What was it?
It's like the, follows the regression line, but it's like way outside.
So, very large or small x values. I will say, like, it doesn't have to necessarily be in the same pattern, but if it's just so high leverage, horizontally far from the data set. So those are more than likely usually horizontal outliers, but if it has a very large or small x value, we call them high leverage.
Oh,
Okay.
horizontally far from the data set.
Say it again.
Horizontally far from the data set.
Horizontally far from the data set, yeah. So far horizontally from rest of data. So influential points. What are they going to be influencing? Slope, y-intercept,
R.
and correlation, right? So if the presence / removal of the point influences, say again,
Presence as like they're there.
yes,
Yeah, I was just clarifying.
presence or removal of the point impacts the slope, y-intercept, or correlation. Okay, so, or the correlation. So, an influential point is any point such that the presence or removal of that point will impact the slope, the y-intercept, or the correlation. You get over there? What's up?
Are all outliers at high leverage?
Say that one more time.
Are all outliers high leverage?
No, because so remember so here we have horizontal outliers. And we have vertical outliers. We saw it earlier. Which set of outliers are higher leverage? The horizontal, right? So typically we're going to talk about horizontal outliers as high leverage, but it also matters how far away it is from the data set. Eventually those vertical outliers, do they start to drastically affect the R? Right. So, and did it start to change the y-intercept? Yeah. So not all outliers are high leverage. The further it is from the data set, the higher leverage it is, but typically a horizontal outlier is a higher leverage. Okay? So what does a horizontal outlier affect? Like what did it do to our line?
The correlation.
It definitely affected the correlation, it affected the slope, so it tilted that line, didn't it? Okay? So horizontal outliers are going to tilt the line. Let's also, actually I do need to clarify, let me show this. So, right now, oh you can't see that, it's frozen. Okay, right now, this data point is horizontally far from the data set, but it's still, and it's also far away from the general pattern, right? Okay. And I guess I should also point this out, Charlie, like here, that's a horizontal and vertical outlier, right? But did it drastically affect R or the slope or the y-intercept? No, because what did it do? It stayed within the pattern. Okay, so if it is a drastic deviation from the pattern horizontally or vertically, then it will be high leverage. That would still be an outlier, horizontal and vertical, right? It's far away from the data set, but it's not changing the slope of the y-intercept because it's in line with the pattern. Okay? Does that
Yeah.
clarify that? Okay. So that's why, what did it do? There it is. That's why when we say like, oh, outliers high leverage, it's only a high leverage, or it's only influential if the presence or removal of the point impacts the slope y-intercept of R. And that would have been a high leverage. So I would also say, I don't know why they have different language for this on mathematic, but they do, and it lines up with the book a good bit. Horizontal outliers are high leverage, they're not necessarily influential. Vertical outliers would not be. Okay, so horizontal outliers tilt the line if outside the pattern. Okay? So the more outside of that pattern that was there, the more it's going to tilt the line. Okay? And again, I will point out, if it's in line with the pattern, what did it do to R? Did it increase R or did it decrease R? If it was in line? Oh, yeah. Right, when it was in line earlier. Okay, so, why are you taking so? Oh man, I got too many things open. There we go, okay. So I'm going to delete this point really quickly. Please don't screw things up. There we go. Alright, so notice that's what my R is right now. What is that, 0.9654? But if I add that point back in, what's my R now? 0.986. So by doing an outlier that's in line with the rest of the pattern, I actually strengthen that linear relationship. It's when that outlier is outside of the pattern that it's going to decrease R. Okay, but tilt the line if the outlier is outside the pattern. A vertical line though, or a vertical outlier, what did that mostly affect?
Just the correlation.
Just the correlation.
Just correlation, it did affect something else
The
though.
y-intercept.
So remember, the horizontal tilted that line, the vertical translated it up and down, right? So translated line up and down, right? Affecting the y-intercept. And I do like the language mathematics says with tilting the line, because if you tilt the line, it's also going to affect slope and y-intercept, right? So when you tilt that line with horizontal outliers, it affects the, it affects both slope and y-intercept. Okay, so this is how outliers or high leverage points influence the least squares regression line.
So when describing the outliers in the free response questions, are we saying that this one is either horizontal or vertical? So if it's high leverage or influential?
So usually, if I will say this again, some of these things have been here in AP Stats forever. Some of these are just the last 2 or 3, maybe 4 years. This idea of a high leverage or influential point is fairly new in AP Stats. What I have seen in the last few years when they started to include it is just asking how would the inclusion of this point or the removal of this point affect the strength of the fit or the slope or something like that, right? So they're not. It is good to know the language, but it's more important for you to visually think, okay, if I put this point in here, how is it going to affect my least squares regression line? That's what they're going to ask you to write about, at least historically. Okay. Okay, formulas for the least squares regression line. There's only 2 big ones, and they're still kind of goofy. And I think I've seen it show up on maybe like 1 multiple choice question. And really it's just on AP Classroom. So what is this equation saying?
The R score is...
Find the standard deviation of y over the standard deviation.
Right, so the slope of the least squares regression line is equal to the correlation coefficient times the standard deviation of your y values divided by the standard deviation of the x values. And if you go, how in the world is that true? No idea, but it's true. I know it is because the formula sheet says so.
How do you calculate the standard deviation in this variable?
calculators. But if I'm using that calculator, guess what?
It's probably gonna get this one anyway.
It's going to give a slope anyways. Now, I will say this, and that's what I'm saying, on a multiple choice question, so they're not going to, let me say it this way, if they're asking you to use this formula, they're not giving you raw data, they may give you the correlation, the standard deviation of y and the standard deviation of x. And then you just plug it into that formula. So you would have to recognize and say, okay, what am I being given? Hey, I'm given correlation, standard deviation of my response variable, standard deviation of my explanatory, substitute into the formula. But once again, I have never actually seen that formula on the AP exam, okay? But it is something given to you. So a thing to remember is sometimes, hey, I'm given bivariate data, I'm not familiar with what this is, let me go see the formula sheet. That's why we need to know this. So just in case this shows up, we gotta know, one, I can look at the formula sheet, I need to know what those symbols stand for. This one is actually a really cool detail. Okay, so the average of my y values equals the y-intercept plus the slope times the average of the x values. So what does that mean? Because that would have been y hat, that'd be x. What does that mean every least squares regression line has to go through?
All of the,
It has to go through the mean of x and the mean of y. So again, this is relating the mean of your x and y using y-intercept and slope. It's not very often used, at least when I say not very often, I've never seen it used on the AP exam. Not on free response or anything like that. But it is good to note, again, hey, I can go see that formula there, and every least squares regression line has to go through the mean. Every least squares regression line has to go through the mean of your x and the mean of your y. That will happen. So that is a good anchor point. So in order for you to get to that least squares regression line, that has to happen. Okay. So I think this check your understanding is probably the closest that I've seen to like what things might be asked on the AP exam using those formula sheets. We don't have a ton of time because I do want to at least go through the next lesson, but I'm going to give you all 5 minutes to work within your small groups on A and B here, and we'll discuss. So just come up with ideas, generate them, talk it out, see what you think's going on, and then we'll discuss as a class afterwards. So let's at least talk about A, because that is definitely the more important one. So remember, an influential observation is one that if it were added, it changes things. Or if it's already there and we remove it, it changes things, right? If I take this point out, how does my line change?
It doesn't.
I would say this, I don't think this line would be the best estimate of those data points that are left
it
behind.
won't get more tilted to the right.
So if I'm looking at this, maybe something, ooh, that's not quite what I would want. Maybe here? That's still a little off. There we go, that's better. That to me is what I think roughly my least squares regression line would look like if I no longer had that point, right? So what did having this point do to that line? The slope, what?
Increase.
The slope was increased. Or, and I do want to clarify, it was made less negative. Okay, so it was made less negative. What happened, what did that point do to the y-intercept? It decreased the y-intercept, right? Remember, it tilted it. Now, thinking about that point, did that point make the data more or less linear? It made it less linear, right? Like, this looks much more linear than if I look at that point being there. So what's it doing to my correlation?
It's
I thought you just said we were observing it if we remove it.
Right, I got you. But it says, how does this point impact? Right? So I'm saying, hey, if I remove it, what would it look like? That's telling me how it impacted. My bad.
That's what we did at the start, and then
I got you. Well, but notice, like, so I'm drawing in that line based on it not being there. Okay, so what did it being there do to that line? Sorry for that confusion. Does that make sense now though, Star?
yes, Keith,
Do we see how these things can impact stuff?
we do.
And you will have multiple choice questions like this on a progress check. Yes,
When
Raina?
you say increasing less, so
since the graph is negative, so it'd be less negative?
Right, that's why I said it makes the slope less negative.
I was just confused about the slope, that how does it get less negative?
Well, if I look at this slope, maybe my slope is, I'm making this up, but like -1. But this slope here might be something like -3/4. That is a less negative number. It's a smaller negative. Okay. But if you wanted to say it increase the slope, you can. All right. Mean and standard deviation are here. Mean and standard deviation are here. And we've got a correlation. So it just says find the equation of least squares regression line. Again, I've never seen this question asked, but I know that my slope is r times standard deviation of y divided by standard deviation of x. I think about slope in order to help me think about this. 0.793 times 1.2 divided by 4.47. And so what would that slope be?
Negative 0.2128.
2128? Okay. 4 decimals, we're fine. Alright, then what was it? Y bar equals a plus b times x bar. Notice how I have everything except for a. So I can fill everything into this equation and solve for a. So my mean for y is just 7.71 is equal to a that I don't know plus negative 0.2128 times my mean for x, which is 8.
Somebody did that.
So solving for a, now I would have my slope and y-intercept. What's up?
I kind of forgot, like, the order of operations. Yeah, you need to add the 0.2, right, first?
To what?
I'm doing
So-
multiplication and division first.
Right.
Yeah.
Okay.
So I would multiply these first. And then I would end up adding it to the other side.
Oh,
to undo.
okay, so, okay.
Is it 600,716?
What? I've got.
Alright, 7.71 is equal to a minus, it's gotta be like a 1.68 or 9.
That's what I got. That's 1.7. Negative 1.7.
But then wouldn't you add that 1.69?
That's what I didn't do.
Did you say that's what I didn't do?
I added the negative on accident.
Ah, gotcha. So a would be somewhere around 9 point, what, 4?
9.4130.
Okay.
309. I got 24.
Y'all, do you think they really care about thousands
It ain't
of
that
decimal?
deep. It ain't that deep.
Yeah, you ain't, don't sweat that. Plus, or I guess minus 0.2128 times x, which really put your context in there, but that would be the formula. Okay? So what's the question? Little ISOP, all good? All I did was I took my A and I took my B, my slope, and filled it into
Thank you so much.
y hat equals A plus B x. Just like off the
How
page.
did you got this slope?
Okay?
How
How did what?
did you got this?
The 9.41?
Yeah, how did you do that?
Right here. So I rewrote that up here, which is a little confusing, but the minus 1.69 added 1.69
Okay,
to get that
Can you
9.41,
interpret
which my numbers are a little off.
can you interpret that?
But I just trusted other people's numbers, huh?
Can you interpret it out?
Interpret what?
Then I'm.
The y-intercept? If someone was assigned 0 practices, we would expect or predict it to take them 9.41 is it minutes to complete the Rubik's Cube,
Oh.
right? Yeah, if they don't know how to solve
Oh,
it,
it's
then it'll
number
take
of
forever.
practices, okay.
Yep, X is number of practices.
That makes
Yes,
sense.
Raina?
Where did you got the negative 0.218 from?
Remember, R,
Oh,
so
the first.
slope is R times, yeah. So that's how we got it. At least I'm trusting y'all to tell me that was the right number, right?
It was.
So we calculate slope from the beginning, then we substitute it into
Be
the
like
other
this.
formula.
Yeah,
Okay.
it was an estimate.
Alright, so here is the next lesson. And so some of y'all have been asking for more practice with some of these things. Well, here you go. We do not have a ton of time to let you just work, but I'm gonna give you all 10 minutes to get as far within this lesson with your small group as possible, okay? So at 1:25, we're gonna start talking about 3.5. Notice this is going back to, can you predict Monster Energy stock value?
Vertical?
Yes, if you want to work on vertical surfaces, you definitely can.
We're waiting for you.
I'm not ready.
Can I erase all of these?
Yes. Okay, so actually I'm going to pause us here because a lot of us have gotten to the backside, and I want to pause before we start talking about that backside really quickly. So, first things first, y'all can look up here. I think everyone got similar responses to this, but we need to check. So, I will say we need to talk about y'all's number 3s. Y'all got very different answers than other people, didn't you?
We got different answers. Oh.
Did.
Hey, I did not write 27.
It's also a negative, it's a negative.
Well, there's another issue.
What is wrong with it?
You don't do 2014.
Yeah. Say again.
You don't do 2014.
You don't do 2014. What are we supposed to do?
14.
After 2014.
As 2000. So be careful because that could throw answers off. Okay. So hey, just be careful. We learn from this. We get better at it. So that is something to be careful about. Again, I will remind you. Hey, pause for a second, ladies. One thing to remember, because we do have the answers over here. The AP readers will read with you. Okay. So AP readers will read with you if you make a mistake in one part, but you use that correctly in later parts, you're good. Alright, so 94.3% of the variability in stock price, so the variability in my response, is explained by the linear relationship with the years after 2000. Beautiful. Number 2, there's our equation. I liked the context. I think everyone wrote it like that. I do like, especially like the year after 2000, exclamation point, woo! But year after 2000. And then we substitute in to get our predicted stock price. So I think everyone who did 14 got that.
Oh, yes.
Okay. So number 4, we got our residual. I think we have residuals somewhere around the room, negative 5.12. Is that right? Okay. So quickly put your answers 1 through 4. Actually, yeah, 1 through 4 down, and we're going to talk about 5. So quickly and efficiently, because we need to talk about the next part of this, the part that was freaking Star out and a handful of others.
Are you not logging this one, Mike? Am I logged?
Hey.
Yeah.
Oh, yeah.
You are?
Yeah, my favorite.
We're talking about it.
Yeah.
Log. Isn't like log E also ln?
Mhm.
Actually.
Man, maybe it's a kill me.
Well,
I still don't know. I know it, it's just I forgot it. I know how to do it, but I don't know what it means. I could easily read through it.
No, I said not.
And just make sure with number 4 you have that.
I know everything in
Right,
there.
It's an easy mistake because we have to know from it.
But I
Wait, why
don't
don't we
know
use 20?
What it was doing.
Oh, because we got that.
Also,
here,
here,
this
this
is
is
more
negative.
like an 8. Yes, it is a negative.
Literally, you're the only one who grows.
Climb someone.
Just make sure. And so,
You wrote that
what
one.
I will say is,
I'm
it's
trying
not
to
like
open
that
my
the
brain.
group over there wrote that full, like
Mine
the.
got switched by my language.
We changed our answer.
I think you made that analogy more
I literally
complicated.
just fixed this answer right here.
It still fit the analogy.
Okay, wait.
That is right.
I do.
Yeah, you put 59.
Yeah, Lorelai.
The questions were so easy.
Wait, why
Because I didn't see the
freaking negative?
That, yes, that is, that negative threw you off.
You said the F word.
Yes, I did. Okay.
So be careful.
She's feeling rebellious today.
Why
She's
what?
on her reward.
Why don't we
Mr. Dickerson.
2014 and just 14?
Because what does the x-axis say? Notice the x-axis here is not 2014 or 20 whatever, it's only
I look like a
years after
soccer
2000.
boy.
So the
No.
prediction, the input is only the years after 2000. So pay attention to the x-axis, right?
You're overstimulating.
I don't want to. Sorry, what did you do?
You know the end of the sitcom where they just freeze frame?
Okay.
Freeze frame. In the final scene, and they're all like back. Like they're all like.
Madeline, which one are you working on?
I'm still writing Kelly.
Wait, can I try to figure out log?
No.
Okay, sorry.
Well, no.
There's your producer price, my bad. That's why I haven't erased it yet. Okay.
Mr. Clay,
Yes, ma'am.
I know you just explained it to me, the thing that throws me off is explain, like, the coefficient of determination. Explain this, just have.
Well, wait, you talking about explain or interpret?
Oh, explained, the coefficient of determination and the interpretation inside the word. We said that is the response variable that is explained by linear relations with explanatory variable.
Right.
It's just, we divide a volume by that, and it's just.
Let's focus on this. I'll answer that question later. All right. Explain why the residual plot indicates a linear model is not appropriate. What is there? What do we see?
It's a
There's a
pattern.
pattern, right? There's a curved pattern in the residual plot, so a linear model is not appropriate. There's a curved pattern in the residual plot, so a linear model is not appropriate. Huh?
Almost parabolic.
In the residual plot, but not in the original.
Yeah, exactly.
Why are you looking at me like that?
Because stars just thought you could almost elaborate.
It looks like, it does look like a parabola, quadratic, yeah.
Can you elaborate?
A parabola, like a pinky. A parabola.
Oh my god.
Mr. Kinney, I remember in Miss Williams' class, I called that an umbilical cord.
I heard
Wait,
about
she
this.
told you that?
Yeah.
I thought she was mad at me.
No, it's hysterical. All right. Okay. So now we need to talk about number 6. So really quickly, all right, I'm going to explain quickly what happened here. So if you look at the original data set, what does this original data set kind of look like?
A curve?
Well, what kind of curve?
Positive parabola.
That looks like an exponential curve to me.
Right.
2 raised to the x, e raised to the x, 10 raised to the x. So if we have an exponential curve, tell me, what's the inverse of an exponential?
An unexponential.
You gotta be kidding me.
Log.
Let's start with
What? Logarithm. Okay?
What?
Eventually you said that. A logarithm. We need to talk more about logarithms, like what a logarithm is, talking after class. But a logarithm is the inverse of an exponential. Now, here's the thing. What I would point out here is this. So if I have 10 raised to the x, okay, that's an exponential. Okay, we good with that?
Yes.
And I take the common log, or the log base 10 of that. These are inverses, so what happens?
It just becomes x.
And y equals x is a line, isn't it?
Yes.
So if we have an exponential and we take the logarithm, what's it going to do to my data set? It's going to make it linear. In the same way, and so this is an overall big idea, if my data set looks like a parabola, a quadratic, an x squared, what would make it linear? Say again? A square root, right? Like if it looks like a parabola, a square root would make it linear. If it looks like a cubic, what would we do? A cube root, okay? So whatever the data looks like, you apply the inverse to make it linear. Same thing of like if we say, hey, it looks x squared, like a quadratic, and I take a square root of that, what am I left with?
X squared.
And no, just x. Isn't that linear? Y equals x, that'd be a line? Okay, so that'd be a linear relationship. So what they do have here is they took the common log of the stock price, and so what I will ask you to do is look at your stock prices tonight, take the common log. So on the front page, you have those stock prices, right?
Yes.
So the ones that are missing, take the common log or log base 10, right? So you don't have to put a base in there. So when it is common log, log base 10. But what I want to focus on is this right here. When I look at this new data set, this data set that is based on taking the logarithms, what does that look like to you?
The regular.
Log.
No, what shape does this data now have?
Linear.
It's linear, right? Remember how I was showing and explaining, hey, logarithm is the inverse, so it's going to create a line? When we take a logarithm of what was exponential data, It linearizes it. It transforms it. Notice, remember, when we transformed by adding and subtracting, multiplying and dividing, it didn't change the shape.
It did.
But if I take a square root, or I take a logarithm, it is going to change the shape. So when you add and subtract, multiply and divide, it doesn't change shape, it just changes center and
I
spread.
think you told us.
But this is affecting the shape. Now, I'm going to leave number 7 for y'all to do tonight, fill in those, but I want to talk about number 8. We need to talk about how to write this equation quickly. Because it would have been the predicted stock price. But do I have
You don't.
the stock price anymore? No.
You have the log.
Right. So the logarithm of the predicted stock price is equal to what?
Negative 0.1533
Plus
plus
0.0871
0.0871.
years after 2200.
Okay, yeah, years after 2000. Notice that is my new model. That's the linear model, but it is the logarithm of, or it's a prediction based on the logarithm. So I should put the hat over the whole thing.
So is it, if it's like a root, if it is a root function, should I square it to?
Mm-hmm. If it's a square root, then you would square.
Oh,
Yeah.
is this linearizing data?
Yes, this is what we call linearizing the data. It was nonlinear. I applied an operation to make it linear. Okay? Now, yeah, just for the last minute or so that we have, I want to briefly talk about number 9. We'll spend some more time on this tomorrow. But if I were to write the linear model to predict the stock prices for 2014, what would I substitute in where?
Can you put for years, I just have to put 14.
Okay? So it'd still be the predicted stock price.
Are we number 9?
Yeah, number 9 is equal to negative 0.1533 plus 0.0871 times 14. Can someone quickly type that in?
1.066.
Thank you. So the common log stock price is equal to 1 point what?
0061. Sorry, 0661.
Okay, thank you. Notice, is that the actual stock price?
No.
What do I need to do to find the stock price?
Square.
I need it, but I don't have a square root. I have a logarithm.
Oh.
So I need to do 10 raised to this power. So I make a base 10, I make this an exponent. That's an exponential, an anti-log. Remember, raising to the 10th would be undoing a 10th root. Then so I do 10 raised to this. So to undo a logarithm, you do an exponential. We will do some more practice with that before tomorrow, but I would look over that maybe in the textbook. But yeah, if you have a logarithm, you write each side of the equation as an exponent.